what do they look like? Notice the subscript. For the terminology here, we always start with alpha 0 is the fully protonated. It is the acid only species for that system. And the subscript 0 refers to no H plus lost. Subscript 1 refers to the first amphiprotic. That would be 1 proton lost. Subscript 2, how many protons lost? 2. Subscript 3, for a triprotic system, they're all gone. So this would be the base only. And that's our conventional nomenclature. So how do I figure all this out? So what we're going to do is figure out an expression for these that is in terms of H plus or pH, which we can measure, and the Ks. And then that species of interest. So species of interest. Whether it's fully protonated, amphiprotic, or base only. So from the Ks, Ka1 is equal to H plus times H2A minus over H3A. So there's my Ka1 statement. I am going to solve this for this one, and then the others are analogous. And I am going to find, I could keep this, this, and this, because that's what I said I was going to keep over here. And I'm going to solve for that. So when I do that, I get H2A minus is equal to Ka1 H3A over H plus. So that's just algebraically rearranging that statement. And now I have an expression that will replace H2A in my C sub A expression. So C sub H3A, this is my total analytical concentration. Remember, it has all these species. So in order to find this denominator term here, I have to find each one of those terms, and then we're going to find each fraction. So Ka2, from Ka2 I have H plus equals Ha2 minus over H2A. If I solve now, I'm going to keep H2A. I'm going to substitute this expression in for here and solve for that term. So I get Ha2 minus is equal to Ka2 H2A over H plus. And if I make this substitution for H2A, I get Ha2 minus equal Ka1, Ka2, K2, H3A over H plus times H plus, or H plus squared. So now I have an expression for that. I'm going to get an expression for each one of these, and that's going to allow me to calculate my denominator term. Now I want from Ka3, H plus,
Can you move it up?
A3 minus over H2A. Can you see where we're going with this? We're just going to keep successive substitution. I'm going to now solve for this is this is supposed to be HA minus, HA2 minus. Oh, let's just clean it up. HA2 minus, okay. So I've got an expression for HA2 minus. I'm going to solve for A3 minus here. I'm going to keep this and this. I'm going to substitute this. And I'm going to have an expression for A3 minus in terms of H's, K's, or pH and K's. So this is going to be A3 minus is going to be equal to, from this, Ka3 times Ha2 minus all over H plus. And now I'm going to substitute this entire expression in for this. Make that substitution. And I get an expression for A3 minus that is Ka1, Ka2, Ka3, H3A all over H plus quantity cubed. Now I'm going to put all that together into one statement. So this expression here will now become this term plus this term plus this term plus this term. So here are my terms. So my C sub A or C sub H3A, my total is H3A plus K1 H3A over H plus plus K1 K2 H3A over H plus quantity squared plus K1, K2, K3, H3A over H plus cubed. For simplicity, I'm just going to start writing H instead of H plus, and I'm going to leave out the brackets. So now when I find alpha 0 is going to be H3A over this total, this denominator here. And look what happens. I'm going to multiply numerator and denominator by H3 cubed, and then I'm going to see what happens. Multiply my numerator and denominator by H3 cubed, and I get plus K1, K2, K3, H3A over, no, that's it. We multiply by H cubed. So look what happens. I can divide numerator and denominator by this H3A, just cancels right out, and I get that alpha 0 is H cubed over H cubed plus K1 H squared plus K1 K2 H plus K1, K2, K3. And that is the simple equation. Okay, that's it. So now, very systematically, every one of these terms, alpha 1 becomes this term over the whole denominator, K1 H squared over, let's just abbreviate this we'll call that D for denominator. So it's just this term over the denominator. Alpha 2 is this next term, so this would be for alpha 1. This term we use for alpha 2 over is equal to K1, K2H over the denominator. And for alpha 3 is equal to K1, K2, K3 over the denominator. Well, what on earth does that look like? Here is a spreadsheet that I made for histidine, the very problem you're working on your quiz. Here are the pKs. Okay, so from the pKs, I can get the Ks. And at pH, because each of those is a function of, except for the very last term, they're all functions of the pH, H plus. And because the denominator is a function of H plus, this one is a function of H plus. This would be alpha 0 calculated at different values of H plus. So alpha 0 would be different values of H plus cubed, and then these terms, substituting in the first K for one of the H's, keeping that, substituting in the second K for another H, and keeping the H, and then finally the third term, I substitute this H out, K1, K2, K3. So it's very systematic. Once you get the pattern, I can now, if I know the pattern, I can write 6 alphas for a hexaprotic acid. It'd be H to the 6th over H to the 6th plus K1 H to the 5th, K1 K2 H to the 4th, K, etc. So there's a pattern to it, and you can derive that for each of these terms. So these are 3 separate functions, or 4 separate functions, alpha 1, alpha 0, alpha 1, alpha 2, alpha 3. This would be for the H3A. This would be for H2A minus, HA2 minus, and finally the base only, A3 minus. And if I plot those, here is what it looks like. And I don't know about you, but the first time I saw things like this, I kind of freaked out. But it's very simple. This curve is this column of data for alpha 0, plotted against pH. This curve is this column of data for H2A minus, for alpha 1, plotted against pH. So this is my alpha 0, alpha 1, alpha 2, alpha 3, as indicated here in the legend. They are separate functions. Each one comes down to the baseline, and we don't have any more discrimination here on the fraction. These are fractions. The highest fraction is 1. That means if a fraction is 1, that means approximately 100% of the material is in this form. So this one relates to H3A, and at this point it's approximately 100%. So when we say it's all the acid, to our ability to discriminate on this axis, that is true. It's up there to 1. This is H2A minus, the fraction of it. So that's, at this point, it is approximately 100%. That would be your first equivalence point. You've taken all of this, removed 1 proton from every molecule, and now you have all of this to a first approximation. Where's my second equivalence point? The next place you see something at about 100%. Well, not quite so good here, but this is HA2 minus. And finally, this is A3 minus. Now, what happens when I've got, this is the fraction 0.5, and I've got 2 things at the same level. What does that mean? What is this? We're at half titration. I've got a 50-50 mix. Or I have a buffer. Not only that, but I have a best buffer.